Hello, in this lecture I will talk about mathematical induction. Mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. A natural number is a positive integer like 1, 2, 3, 4, 5, 6, 7, etc. We have two stages in mathematical induction. In the first stage, we will check whether the statement is true for n that equals to 1, and only after we passed the test, that is to say, we verified that the statement is true for n that equals to 1, we will proceed to the second stage. That is to say, in the second stage, we will assume that the statement is true for n, and we will prove it for n plus 1. And actually, in order to prove the statement that the statement is true for n plus 1, we will rely on our assumption that the statement is true for n. So we will create in the second stage two equations. The first equation will be the expression of the statement for n, and it will be the induction hypothesis, or the induction assumption that that statement of that expression of the statement is true for n, and when we rely on this assumption, we will prove that the statement for n plus 1 is also true. So we will also create a second equation, that is to say, the expression of the statement for n plus 1, and we will prove that that expression for n plus 1 of the statement is true when we rely on our assumption that the statement for n is true. Okay? When we rely actually on the induction hypothesis that the statement for n is true. Okay, so actually we can summarize that in the first stage we will check whether the statement is true for n that equals to 1, and only after we passed the test and the statement is indeed true for n that equals to 1, we will proceed to the second stage. That is to say, in the second stage we will assume that the statement is true for n, and then we will prove that the statement also true for n plus 1, and we will prove it by relying on our assumption that the statement is true for n, or by relying on the induction hypothesis. Okay, so now I will explain what is the logic behind the mathematical induction's proof. Okay, you should remember that in the first stage we verified that the statement is true for n that equals to 1, while in the second stage we actually uh, proved that if the statement is true for n, then it must be true for n plus 1. So we can say that now we know for sure that the statement is true for n that equals to 1, and for our general proof in the second stage that if it is true for n, it also must be true for n plus 1, we can say that we know that the statement is true for n that equals to 1, and therefore it also must be true for n that equals to 1 plus 1, that is to say for n that equals to 2. Because we proved in general that if it is true for n, it also must be true for n plus 1. And we know for sure that it is true for n that equals to 1, so it also must be true for n that equals to 1 plus 1, that is 2. So in this way we actually proved that the statement is also true for n that equals to 2. And then we will repeat on the same process in order to prove that the statement is also true for n that equals to 3. Because we can say that now we know for sure that the statement is true for n that equals to 2, and for our general proof that if it is true for n, it also must be true for n plus 1, we can say that now we know for sure that the statement is true for n that equals to 2, so it also must be true for n that equals to 2 plus 1, that is 3. So in this way we actually proved that the statement is also true for n that equals to 3. And then we will repeat on the same process in order to prove that the statement also true for n that equals to 4, because now we know that for sure that the statement is true for n that equals to 3, and for our general proof, that if it is true for n, it also must be true for n plus 1. We can say now we know that it is true for n that equals to 3, and therefore it must be also true for n that equals to 3 plus 1, that is 4. And that is true for our general proof that if it is true for n, it also must be true for n plus 1. And now we know for sure that it is true for n that equals to 3. So from our general proof, we can say that it also must be true for n that equals to 3 plus 1, that is 4. Okay, so in this way we actually proved that the statement is also true for n that equals to 4, and so on. In the same way we will prove that the statement is true for n that equals to 5, to 6, to 7, etc. So that is the logic behind the mathematical inductions proof. Okay, so now in order to clarify the topic, I will give you 2 examples. We will start with the first example. One plus 2 plus 3 equals to plus n plus n equals to n times n plus 1 divided by 2. So we actually have to prove that 1 plus 2 plus 3 plus 4 plus n equals to n times n plus 1 divided by 2, and that this statement is true for all the natural numbers. Okay, so we will start with the first stage. It is to say, we will check whether the statement is true for n that equals to 1. Okay, so this side of the equation we will have only 1 because n equals to 1. 1 equals, in the other side of the equation we will have n times n plus 1 divided by 2, and n equals to 1, so it will be 1 times 1 plus 1 divided by 2 equals to 1 times 1 plus 1 is 1 times 2 divided by 2. 1 times 2 is 2. 2 divided by 2 is 1. So 1 equals to 1. So we actually passed the first test. We verified that the statement is true for 1 because in this side of the equation we have 1, and in the other side of the equation we have n times n plus 1 divided by 2, and n equals to 1, so it is 1 times 1 plus 1 divided by 2, and 1 times 1 plus 1 is 1 times 2 divided by 2, so, and 1 times 2 is 2. 2 divided by 2 is 1, so 1 equals to 1. So we found out that the statement indeed is true for n that equals to 1 because we have here identity. This side of the equation equals to the other side of the equation, so the statement is indeed true for n that equals to 1. So therefore we can proceed to the second stage, and in the second stage we actually will assume that the statement is true for n, and we will prove it for n plus 1. So we will create first equation, the expression for n. The expression for n is exactly the same expression of the original statement, 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. Okay, so it is exactly the same expression. So we will copy it, 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So this equation will be the induction's hypothesis, because we actually assume that this expression of the statement for n is true, and when we rely on this assumption that this expression of the statement for n is true, we will actually prove that the expression of the statement for n plus 1 is also true. So now we will create the expression of the statement for n plus 1. So the expression of the statement for n plus 1 will be 1 plus 2 plus 3 plus n. You should remember that is the expression of the statement for n plus 1, so it will be plus n plus 1 because it is the expression for n plus 1, so we must also add numbers until we arrive to n plus 1, and it must be include the n plus 1. Okay, so it will be 1 plus 2 plus 3 plus n plus 1 plus n plus 1 equals to n equals to, in the original expression for n, we have in the other side of the equation n times n plus 1 divided by 2, but here we want to create the expression for n plus 1, so wherever it is written here n, we will write n plus 1 because it is the expression for n plus 1, so we will replace n by n plus 1. We will substitute n by n plus 1 because we now creating the expression for n plus 1. So instead of n in the original statement, we will write n plus 1 because it is the expression for n plus 1. So equals to, instead of n, we will write n plus 1. So if in the original statement is written n, we will write n plus 1 times n plus 1. So it will be times n plus 1. So instead of n, we will write n plus 1, and in the original expression we have n plus 1. So here we have n plus 1 plus 1 because instead of n we wrote n plus 1, and it is in the original statement plus 1, so we must add 1 also in the expression for n plus 1, so it will be n plus 1 plus 1. Okay, and all divided by 2. So, but n plus 1 is n plus 2, so we will write it down. N plus 1, 1 plus 2 plus 3 plus n plus 1 equals to n plus 1 times n plus 2, all divided by 2. Okay, so the second equation is the expression for n plus 1. As you can see, while the expression for n, we added numbers until n, for the expression for n plus 1, we add numbers until n plus 1. The expression for n plus 1 must include also n plus 1. So the expression for n plus 1 is 1 plus 2 plus 3 plus n plus n plus 1 equals to wherever it is written n in the original expression for n, we will write n plus 1, because in the expression of n plus 1 we want to create expression that is for n plus 1. So instead of n that is written in the original expression, we will write n plus 1. We will substitute n by n plus 1. Okay, so here it equals to n plus 1 times n plus 1 plus 1, because this is the expression for n plus 1. So wherever it is written n in the original expression, we will write n plus 1. But in the original expression, it was n times n plus 1. So in the expression for n plus 1, we will write n plus 1 times n plus 1 plus 1. Okay, because we add 1 to n plus 1, so it will be n plus 1 plus 1, and n plus 1 plus 1 equals to n plus 2, so in total it will be here n plus 1 times n plus 2 divided by 2. And we must prove that this expression, the second expression, is true when we rely on our assumption that the expression for n is true. We will rely on the induction's hypothesis that the first equation for n is true. Okay, so we have to prove that the expression for n plus 1, the second equation, is also true. So in order to prove the second equation, we should look on this expression 1 plus 2 plus 3 plus n, and as you can see, 1 plus 2 plus 3 plus n is exactly identical to this expression, so they are identical to each other, the expressions that are in the green color. In both we have 1 plus 2 plus 3 plus n, but in the second equation we see that 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So this expression equals to this expression, and this expression equals to this expression. So we can say that this expression also equals to this expression, and therefore we can substitute 1 plus 2 plus 3 plus n by n times n plus 1 divided by 2, because they are equal to each other. Okay, so we will do the change now. We will substitute this expression by n times n plus 1 all divided by 2. Okay, so we substituted these two expressions because they are equal to each other, and the rest of the second equation we will copy it as it is. Okay, so it will be n plus 1 equals to n plus 1 times n plus 2 all divided by 2. Okay, so we copied it from this row to this row, and the only change we did in this row, the only change that we did in this row, actually we substituted this expression by n times n plus 1 divided by 2 because they are equal to each other, so we can substitute between them. And the rest of the equation 2 is the same as equation 2 here. Here it is n plus 1, we copied it n plus 1 to here, and equals to n plus 1 times n plus 2 divided by 2, so it is also the same expression, n plus 1 times n plus 2 divided by 2. Okay, so we have to prove that this second expression for n plus 1 is true, and in order to prove that it is true, we can see that in the equation we have n plus 1 in both sides of the equation, so we can divide this equation by n plus 1, or we can divide both sides of the equation by n plus 1, because we have n plus 1 in both sides of the equation. So we will divide the equation by n plus 1. And actually we will get that n times n plus 1 divided by n plus 1 is n, and n is divided by 2 plus n plus 1 divided by n plus 1 is 1 equals to n plus 1 times n plus 2 divided by n plus 1 is n plus 2, and it is divided by 2. So we'll repeat again. N times n plus 1 divided by n plus 1 is n, and we divided it by 2, and n plus 1 divided by n plus 1 is 1, and n plus 1 times n plus 2 divided by n plus 1 is n plus 2, and we divide it by 2. So we have to prove that this second equation for n plus 1 is true. So we can separate n plus 2 divided by 2 to two parts. It will become n divided by 2 plus 2 divided by 2. Okay, so we will write it down. So, as you can see here, n plus 2 divided by 2, when we separated it to this expression to two parts, it becomes n divided by 2 plus 2 divided by 2. Okay? And 2 divided by 2 is 1, so we will write it down. So we got here an identity there is an identity here, that is to say n divided by 2 plus 1 equals to n divided by 2 plus 1. So therefore we actually proved that the second equation for n plus 1 is true. or we actually proved that if the original statement is true for n, then it must be also true for n plus 1. Okay? So, in the second stage, I repeat, we proved that if the statement is true for n, it also must be true for n plus 1. Okay, so we can summarize that in the first stage we verified that the statement is indeed true for n that equals to 1, while in the second stage we proved that if the statement is true for n, it also must be true for n plus 1. And actually in this way we proved that the original statement, this original statement 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2, this statement is true for all the natural numbers, because in the first step we verified that this statement is true for n that equals to 1, and in the second stage we verified if this statement is true for n, it also must be true for n plus 1. And as I've already explained in the beginning of the lecture, in this way we actually verified that this statement is true for all the natural numbers, because we can do the process that will show you that the statement is true for all the natural numbers, and we will start with the fact that n equals to 1. The statement is true for n that equals to 1, and we actually proved in general that if it is true for n, it also must be true for n plus 1. So now that we know that it is true for n that equals to 1, it also must be true for n plus 1, or for 1 plus 1, that is to say for 2. Okay, because we have the general proof that if it is true for n, it also must be true for n plus 1. So we know that it is true for n that equals to 1, so it also must be true for 1 plus 1 that equals to 2. And after we know that the statement is true for n that equals to 2, we can in the same way prove that the statement is true for n that equals to 3, because we know for sure that the statement is true for n that equals to 2, and for our general proof that if it is true for n, it also must be true for n plus 1, we can say that because of the fact that the statement is true for n that equals to 2, it also must be true for n that equals to 2 plus 1, according to our general proof that if it is true for n, it also must be true for n plus 1. For that reason, the statement is also true for n that equals to 3. And then we will repeat on the same process in order to prove that the statement is also true for n that equals to 4, because now we know that the statement is true for n that equals to 3, and it also must be true for n that equals to 3 plus 1, according to our general proof that if it is true for n, it also must be true for n plus 1. So now that n equals to 3, it must be also true for n that equals to 3 plus 1, that is 4. So in this way we proved that the statement is also true for n that equals to 4, and so on and so on. In the same way we will prove that the statement is true for n that equals to 5, 6, 7. So in this way we actually proved that this statement is true for all the natural numbers. Okay, so we finished with the first example. Now we will move to the second example. The second example is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n square times n plus 1 square, all divided by 4. So we have to prove that this statement is true for all the natural numbers. Okay, so we will start. The statement is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square, all divided by 4. We have to prove that this statement is true for all the natural numbers. So we will start with the first stage. In the first stage, we will check if this statement is true for n that equals to 1. Okay. So in this side of the equation we will have only 1 to the power of 3 because n equals to 1 equals, in the other side of the equation we have n squared times n plus 1 squared divided by 4, and n equals to 1, so it will be 1 squared times 1 plus 1 squared, because it is n plus 1, so it is 1 plus 1 square divided by 4. So 1 square equals to 1 times 1 plus 1 is 2, and it is actually 2 square, all divided by 4 equals to 1 times 2 to the power of 2 is 4 divided by 4. 1 times 4 is 4. 4 divided by 4 is 1. So we repeat again what we have done here. We actually check that this statement is true for n that equals to 1. So in this side of the equation we have only 1 to the power of 3, so we copy it here because n equals to 1, so we will have here only 1 to the power of 3, and on the other side of the equation we have n squared times n plus 1 squared divided by 4, and n equals to 1, so it is 1 squared times 1 plus 1 squared divided by 4, and 1 squared equals to 1, and 1 plus 1 square is 1 plus 1 is 2, so it is actually 2 square divided by 4, and 2 square is 4, so it is 1 times 4 divided by 4, and 1 times 4 is 4, and 4 divided by 4 is 1. So here we have actually an identity because 1 to the power of 3 equals to 1, so it is 1 equals to 1. So in this way we actually proved that this statement is true for this statement is true for n that equals to 1. So we passed the first test. That is to say, we verified that the statement is true. This statement is true for n that equals to 1. So therefore we can proceed to the second stage. That is to say, we will assume that this statement is true for n, and then we will prove that the statement is true also for n plus 1. Okay? So actually, in the second stage, we will create two equations. The first equation will be this original statement for n. So this statement is when you create the statement for n, is actually the same, exactly the same of this statement. Okay, so the statement for n is the same as the original statement, so we copy it. 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 plus plus n to the power of 3 equals to n square times n plus 1 square, all divided by 4. So the expression for n of the statement is exactly as the original statement. That is to say, it is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared divided by 4. So we assume that this statement is true, so we will call it the induction's hypothesis or induction's assumption. Okay, this statement will be called induction's hypothesis. Or induction's assumption. That is to say, we assume that the statement or the expression of the statement for n is true. This is the expression of the statement for n, and we assume that this statement is true. We assume that equation 1 is true, and when we rely on that assumption, we will prove that the expression of the statement for n plus 1 is also true. So now we will create the expression for the statement for n plus 1. It will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3. It is expression for n plus 1, so we will add numbers until n plus 1. We have n to the power of 3, and then we will have n plus 1 to the power of 3 equals, so in the original statement we have n squared times n plus 1 squared divided by 4, and in the second equation, we actually create the statement for n plus 1. This is the expression of the statement for n plus 1. So wherever it is written n in the original statement for n, wherever it is written n, we will substitute it by n plus 1 because we want to create the expression for n plus 1. So instead of n, we will write n plus 1. So in the original statement we have n squared times n plus 1 squared divided by 4. So instead of n, we will write n plus 1. So it will be, instead of n square, we will write n plus 1 square. And instead of n again, we will write n plus 1. And in the original statement we have n plus 1. So in this statement for n plus 1, it will do n plus 1 plus 1 because we substituted n by n plus 1. So instead of n, we wrote n plus 1, and in the original statement we have n, we have 1, so we will add also 1, so it will be n plus 1 plus 1, all divided by 2. So, and squared. So, the expression for n plus 1 that we have to prove that it is true will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3 equals to n plus 1 square times n plus 1 plus 1 square divided by 2. We actually substituted n by n plus 1. In the original statement we add n, and instead of n we wrote n plus 1 for the expression for n plus 1. Okay, so now we know that n plus 1 plus 1 equals to n plus 2, so we write it down. So this row is exactly like this row. The only change that we did, we wrote that n plus 1 plus 1 square equals to n plus 2 square, because n plus 1 plus 1 equals to n plus 2, okay? So we have to prove that the second equation, that is the expression of the statement for n, is true. So we will do the same process as we did in the first example. We should look on this expression in the green color. We have 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3, and this expression is identical to this expression. It is also 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3, and they are identical. The expression in the green color are identical, so but this expression equals to n squared times n plus 1 square divided by 4. Okay, so because of the fact that this expression is identical to this expression and this expression equals to this expression, so we can say that this expression is also equals to this expression. Okay, they are equal to each other, so we can substitute one by another. So we'll do it now. So instead of 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3, we will write n squared times n plus 1 squared divided by 4. We substitute one by another because they are equal to each other. Okay, so we write n squared times n plus 1 square all divided by 4, and the rest part of the equation we will copy it as it is. The only thing that we will do is to change this expression by n squared times n plus 1 squared divided by 4, and we will copy the rest of the equation as it is. Okay, plus n plus 1 to the power of 3 equals to n plus 1 square times n plus 2 square all divided by 4. Okay, we actually substituted this expression by this expression. We can do it because they are equal to each other, because this expression equals to this expression and this expression equals to this expression. So we can say that this expression also equals to this expression, so we can substitute one by another. So we substituted it and we copied the rest of the equation as it is. Here it is n plus 1 to the power of 3, we copied it here, and here we have equals to n plus 1 squared times n plus 2 squared divided by 4. So we copied this expression as it is to here. So we actually have to prove that this expression for n plus 1 is true. In order to prove that this expression is true, we will divide both sides of the equation by n plus 1 square, because we have n plus 1 square in both sides of the equation. So n squared times n plus 1 squared divided by n plus 1 squared equals to n squared, and we divided it by 4, and n plus 1 to the power of 3 divided by n plus 1 squared will be n plus 1, and n plus 1 squared times n plus 2 squared divided by n plus 1 square will be n plus 2 square, and we divide it by 4. Here we can multiply both sides of the equation by 4. So we get that n squared plus 4 n plus 1 equals to n plus 2 squared. So we multiplied both sides of the equation by 4. So n squared divided by 4 times 4 is n squared, and n plus 1 times 4 multiplied by 4 will be 4n plus 1, and n plus 2 squared divided by 4 times 4 will be n plus 2 squared. So now we will open the brackets on both sides of the equation. So we get n squared plus 4n plus 4 equals to n plus 2 times n plus 2. So we open the brackets, n squared is n squared, and 4 times n is 4n, 4 times 1 is 4, all equals to n plus 2 squared. So n plus 2 squared is actually n plus 2 times n plus 2, and we will open the brackets again. So after we open the brackets, we got that n times n is n squared, and n times 2 is 2n, and then we have 2 times n is also 2n, and 2 times 2 is 4. So here we have n times n, and 2n plus 2n is 4n. So we write it down. So we have here an identity. So here we copy it here as it is. This is n squared plus 4n plus 4 equals to n squared. 2n plus 2n is 4n, and we have here 4, we copied it here. So we have here identity, n squared plus 4n plus 4 equals to n squared plus 4n plus 4. So we actually proved that the second expression for n plus 1 is true, or we proved that if this statement is true for n, that it also must be true for n plus 1. So in the first stage we proved that this statement is true for n. We verified that this statement is true for n, while in the second step we proved that if this statement is true for n, it also must be true for n plus 1. So in this way we proved that this statement is true for all the natural numbers. And the expression of white is true for all the natural numbers. I explained it in the first example, so I will not repeat it. And we can summarize the lecture and say that mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. And a natural number is a positive integer like 1, 2, 3, 4, 5, 6, 7, 8, and so on. We have two stages in mathematical induction. In the first stage, we will check that the expression is true for n that equals to 1, and only if we passed that test and we verified that the statement is indeed true for n that equals to 1, then we can proceed to the second stage. And in the second stage, we will assume that the statement is true for n, and we will prove that that statement is also true for n plus 1. And we will rely on our assumption that the statement is true for n, in order to prove that the statement is also true for n plus 1. So we will create two equations. The first equation will be the induction's hypothesis, or the induction's assumption. That is to say, it will be the statement for n, the expression of the statement for n, and we assume that this expression is true, and when we rely on this assumption, we will prove that the statement is also true for n plus 1. So we will create the expression for n plus 1, and we will prove that this statement is true. The expression for n plus 1 is true, and we will do it by relying on our assumption that the statement is also true, that the statement of for n is true, and we proved that the expression for n plus 1 is true by relying on our assumption that the statement for n is true. Okay, and I will summarize briefly how we can deduce from the two stages of the proof that the statement is true for all the natural numbers, because in the first stage we verified that the statement is true for n that equals to 1, while in the second stage we proved that if the statement is true for n, then it must be also true for n plus 1. So we actually can say that now that we know that the statement is true for n, it also must be true for n that equals to 1 plus 1. That is to say, for n that equals to 2, because we proved in general that if the statement is true for n, it also must be true for n plus 1. And now we know for sure that the statement is true for n that equals to 1. So it also must be true for n that equals to 1 plus 1, that is 2. And we will repeat on the same process in order to prove that the statement is true for 3. Because we know now that the statement is true for n that equals to 2, and according to our general proof that if it is true for n, it also must be true for n plus 1, we can say that the statement is also must be true for 2 plus 1. We know that the statement is true for 2, so now so it must be also true for 2 plus 1, that is 3. And we repeat on the same process in order to prove that the statement is true for 3 and 4 and 5 and 6, etc. So in this way we actually proved that the statement is true for all the natural numbers. Okay, thank you very much.